Okay, guys, good afternoon. We'll go with the next problem. And also, this is going to be the last class for this module. Okay, probably this is not going to take the whole hour. So whatever time it takes, let it take. Okay, so a joist cutting is used as bracket to support a factor load of 200 kilonewton. Okay, factor load, that is Pu equal to 200 kilonewton. So you don't have to multiply this value by 1.5. So it is welded to the column flange as shown in figure. Compute the size of the fillet weld. So that is the problem. So Charun, what is the time? Network issue, right? You're always late. So coming to this, a joist cutting, this is the bracket we are using. This is a joist cutting. Joist cutting means it is a piece of I section. Okay, and the piece of I section is used as a bracket to support a load of, that is a design load of 200 kilonewton. Okay, so we need to find out what is the size of the weld required, and as far as the lengths of the welds are concerned, so it is already fixed 120 millimeter width of the weld. Here it is 320 millimeter weld. Okay, so if not given, if the lengths or height of the welds are not given, what you can do is, so go to this section. What is this? This section is ISHB 400 at 759.3 Newton per meter. Look here, this is the joist. This is the bracket made of a joist. Okay, so go to the steel table and find out what is the width of the flange. So you have to select the length of the weld at the top and at the bottom in such a way that the length should not exceed the width of the flange. And of course, the depth of the flange at the web portion is going to be this much. So what is this length, or what is this height? So you are going to fix it by deducting this side, that is the thickness of the flange, minus R1 distance, that is the radius of this quadrant of a circle. Okay, on both sides. So that means total height minus of flange thickness minus of R1 value, 2 times of that. Finally, it will give you this height and provide that much of weld. Okay, so that way you can fix it, but in this problem it is already given. So where are you get all those R1 value, thickness of the flange and all those things, you are going to get in the steel table. Okay, and this is, again, this is the column. Okay, what is the column? ISHB 450 at 855 Newton, 4 Newton per meter. So what we have done is, see, when you look at the connection, so this is type 2 connection. The reason being that the plane of the weld, which is perpendicular to the paper or the screen, is different from the plane of the load. So this is called type 2 connection. As a result, the weld is going to be subjected to shear as well as the normal stress. So the shear stress acts like this, downwards. So it is going to be uniform over the entire area of the throat of the weld. And as far as F2 is concerned, it acts away like this. For this portion of the weld, anything below the neutral axis, the weld is going to be subjected to compression. But we are only worried about the tension part. F2 happens on the top weld. Okay, so I have written the dimensions or the sizes of the weld along with their lengths here. So our main aim is to find out what is the size of the weld. So if you look here, I've taken the size of the weld here and here as T suffix T. Here I have taken 2 times of that value. The reason is because when it is subjected to bending like this along with the shear due to PU load, so this is going to be subjected to maximum stress. That is, each unit area of the top weld is going to be subjected to maximum stress by virtue of the location farthest from the neutral axis. Okay, so of course this weld is also subjected to tension, but not as much as this. So because of that, what I have done is I have provided more weld, and the weld size is 2 times the weld size of this one. Okay, the vertical weld. So of course, let TT be the thickness of the throat for this vertical part of the weld. So let us provide 2 times TT throat thickness for the flange weld. This is the flange weld and this is the flange weld. Okay, as it takes greater moment. So of course, we have this formula. See, when this is F1, when this is F2, the resulting stress is going to be acting in this direction. Okay, and this is given by square root of F1 square plus F2 square. So we need to find out what is F1 and what is F2. So to find out what is F1, so that is the direct shear stress. That is equal to factored load divided by the throat area. So factored load is PU, that is equal to 200 kilonewton multiplied by 1000 to convert the value into Newton, divided by the total throat area. So that is this throat area 2T times 120 millimeter is the width. Look here, 2T times 120 millimeter plus this TT multiplied by 320. And multiply the whole thing by 2 because we have 2 such welds, 2 vertical welds and 2 horizontal welds. So finally we got the throat area as this. So design load divided by the throat area will give you the design shear stress to which the weld is subjected to. Here TT is the unknown, that is the thickness of the throat. Next, let us find out what is normal stress, okay, due to bending. Okay, F2 is the value. We know the equation, we have this equation, bending equation from strength of materials, that says E by R equal to M by I equal to F by Y. So E by R, of course, we don't use it. We only use M by I equal to F by Y. So this is F. Y comes here, M, this is M divided by I. That is the moment of inertia of the weld section. Okay, moment is PU by E. So PU is known, that is given. And what is E? E is the eccentricity. Eccentricity is already given. 170 millimeter is the eccentricity. So coming back to this equation, PU is known, E is known, and Y max is the distance of the farthest weld from the neutral axis. Okay, and farthest weld we need to consider because that is the weld which is going to be subjected to maximum stress when compared to any other interior portion of the weld. Okay, so Y max equal to D by 2, where D is the total depth of this section divided by 200 millimeter. That means if this is the neutral axis, to the bottom of the weld, it is going to be 400 divided by 2, that is 200 millimeter. Okay, of course, we should consider until the center of the weld from the neutral axis. But here we are ignoring the thickness of the weld in all our calculation because the contribution of this as far as distance is concerned is negligible. So we take only this to the bottom of the weld. Okay. So that is Y max is known. So IXX, one second. Coming to IXX, that is the moment of inertia of the weld about the horizontal axis. So that is, if I take this weld first, so moment of inertia of this weld about this axis is given by moment of inertia of this weld about its own parallel centroidal axis plus area of this weld and square of the perpendicular distance between those two axes. One is the major axis and the other is the individual parallel axis. That is the axis which is passing through the centroid of this weld which we are considering. Okay, so that is 120 multiplied by 2 tq by 12 plus, when you apply parallaxis theorem, 120 multiplied by 2 t suffix t will give you the throat area and square of the perpendicular distance between those two axes. So that is 400 by 2. So multiply the whole thing by 2 because we have two such welds. One is at the top and the other is at the bottom. Okay. So of course, as I said, please develop the habit of ignoring small things. So cube of any small things when compared to other values, okay, is going to be insignificant. So you can ignore it. Okay, even if you include it, it is not going to make much difference. Here we are ignoring it because if we don't ignore, whatever the final equation we get is going to be in terms of t suffix t cube. So then you will have a cubical equation. You will have to solve it. Finally, you will end up getting the same value as the value you would have got by ignoring it. So it is better you ignore it just to make your life comfortable. Okay. Next, we have one more weld here. That is this one. So TT multiplied by this 320 cube by 12. That is TT multiplied by 320 cube by 12 multiplied by 2 because we have two such vertical welds. Plus if you apply parallaxis theorem, because the centroid of the whole area XX is coinciding with the horizontal centroid of the individual weld area, then there is no perpendicular distance between those two axes. So that is 0. Therefore, AH square, where H is the distance between those two axes, is 0 in this case. So that's why second part plus something like this I have ignored. Okay, so that does not come into picture. Finally, I got IXX value equal to this much. So in terms of TT. So now I have all the values to substitute in this equation. PU is known, E is known, IXX is known now, Ymax is known. So substitute all the values in this equation. So I got the value of F2 equal to this much. Okay. Next, we have the formula, this formula. So substitute the values of F1 and F2. So we got the value of F equal to this much, 328.52 divided by TT Newton per millimeter square. So F is the stress to which the critical weld, that is shear, the weld throughout the length per unit area is going to be subjected to. So the weld throughout the length is the critical weld. Okay. So if you consider the unit area, so F is the force to which that unit area is subjected to, and that F and that is the maximum value. If you consider any weld inside, so the value is always going to be less than F. Okay, we have to consider the highest value. So that F is this. Okay. So I'm going to equate this with the design strength of the weld. So how do you find out the design strength of the weld? As usual, page 79 of the code book. Go and you'll have this formula. where FW1 equal to this much. So, and gamma MW, if nothing is given, whether it is shop welded or field welded, you assume some welding, shop welding or field welding. Here I've assumed this as field welding. So when you assume it as field welding, this gamma MW equal to 1.50 as per table 5 on page 30 of the code book. Okay. So after substituting the value, we get FWD equal to this much. Now I'm going to equate, excuse me, I'm going to equate the stress developed at the extreme weld due to the design load with the design strength of the weld. So that way I got thickness of the throat equal to 2.08 millimeter. Okay. Then if that is the case, what is the size of the weld? TT equal to KS. So therefore S equal to 2.97 millimeter. That is the weld size you can provide in the vertical weld, and 2S is, that is 6 millimeter is the weld size we are going to give in the horizontal portion of the weld. However, if you open page number 78 of the code book, please open it. So page 78, table 21. Are you there on that page? So there, table 21. So minimum size of first run or of a single run fillet weld. So we have to provide certain minimum size. That depends on the thickness of the two parts which we are trying to connect. So if you take this weld, again I will go up. So this is the thickness of the throat, and the weld size according to the calculation we got equal to 2.97, say 3 millimeter we got. But we are connecting this web, that is this web, to the flange. So what is the flange thickness? Flange thickness is 13.7 millimeter. What is the web thickness here? The web thickness here is 9.1 millimeter. So where did we get that value? So please open the steel tables by KLV Ramu. That's what I am referring. Okay, open page number 2 initially. So that goes up to ISMB. Then go to page number 4. Go to page number 4. So are you on that page? Hopefully so. So if you look at the bracket is ISHB 400, 759.3 Newton per meter. Okay. So on page number 4, if you keep going down, you will get ISHB 400, two varieties or two types of ISHB 400. Out of this, we'll have 759.2 Newton per meter, 806.3 Newton per meter. That is the weight of the I section per unit length, that is per meter. Okay. So here it is given as for ISHB 400, 759.3 Newton per meter. So go to that ISHB 400, 759.2, and if you go horizontally, you get the thickness of the web equal to 9.1 meter. Sorry, 9.1 millimeter. So that's what I have written here, 9.1 millimeter. So we are trying to connect this web of thickness 9.1 millimeter to the flange of this column. So what is this column? ISHB 450 at 855.4 Newton per meter. Again, on the same page, if you go just below it, you'll see ISHB 450, 855.4. Of course, ISHB for 450, we have two types. We have to go for 855.4. And if you go horizontally, the thickness of the flange you get equal to 13.7 millimeter. Are you getting it? So 13.7 millimeter, it is 9.1 millimeter is the smaller thickness, and 13.7 millimeter is the thicker plate thickness. So again, if you go back to the code book and go to the table, it says thickness of thicker part. That means we have to go for the second line. It says over 10 millimeter, below 20 millimeter, up to and including 20 millimeter, less than equal to 20 millimeter, and greater than equal to greater than 10 millimeter. That means thickness of the thicker part. So here the thickness of the thicker part is 13.7 millimeter is the thickness of the thicker part, which falls between 10 and 20 in the table of the code book. So what is the minimum size of the weld we have to provide? We have to provide 5 millimeter size weld. Even though by calculation we got 2.97 millimeter weld here, according to the code, the minimum size of the weld we have to provide is 5 millimeter. I hope you got this. So that's why I have provided 5 millimeter. Next, so this is for this weld. How about for this weld? So 2.97 is the weld size according to the calculation we got here. So 2 times of that equal to 5.94, that is 6 millimeter. That is a 6 millimeter weld we are providing at the top. That means we are trying to connect the flange of this bracket to the flange of this. So what is the thickness of the flange of this bracket? Again, from the steel table, it is 12.7 millimeter, and 13.7 millimeter is the thickness of this flange. So thicker of these two flanges is 13.7 millimeter. Okay, again, if you go to the table 21 on page 78 of the code book, again that thickness of the thicker plate falls between 10 and 20. So the minimum size of the weld is 5 millimeter. So the minimum size of the weld is 5 millimeter for this weld. However, we are providing not 5 millimeter. As per the calculation itself, we got 5.94. Therefore, we are giving 6 millimeter, which is greater than 5 millimeter, which is the minimum. Okay. Here, for the vertical weld, we are providing the minimum size of 5 millimeter, even though we got the size of the weld as 2.97. For the horizontal weld, we got minimum value as if 5 millimeter, but according to the calculation, we got 6 millimeter. So we are providing that. I hope this is clear to you. So with that, we'll go with the next problem. So the next problem says, determine the suitable weld size for the connection shown in figure. Okay, so this is the figure. This is one of the examination problems. So this is an I section, ISHB 300 I section at 630 Newton per meter. So from the steel table, I got the thickness of the flange equal to 10.6 millimeter. And for this angle, so it is ISA 125 by 95 by 12 millimeter with longer leg, that is 125 millimeter leg is connected to the flange of the I section, and this is serving as a bracket support, and this is supporting a load of service load of 100 kilonewton. Okay, and we need to design the welded connection to withstand the service load of 100 kilonewton. Please hold on for a second. Okay, so again, this is type 2 connection. So P is given, this is the eccentricity 60 millimeter. So P is 100 kilonewton. Design load is PU equal to 1.5. That is the load factor multiplied by 100. That is equal to 150 kilonewton. Eccentricity is 60 millimeter. Again, we don't know the thickness of the weld. As usual, we are going to assume that the thickness of the throat is TT. Okay. And we are going to provide the weld here and of course here. So what is the width of the weld? That is 250 millimeter. Okay. And again, it is 250 millimeter here. Why 250 millimeter and 250 millimeter? The maximum we can go up to is 250 millimeter. Of course, as far as the length of the angle is concerned perpendicular to the paper, so it can go to any length. But there is a limit for ISHB 300. So what is the flange width of this I section? That is ISHB 300. So from the table, we have two types of ISHB 300, out of which 630 Newton per millimeter. So width of the flange is 250 millimeter. So maximum length or maximum width of the weld we can go up to is 250 millimeter. That's the reason why I have taken 250 millimeter here. Okay. So I need to find out what is the weld size. As usual, direct stress PU divided by the total throat area. So PU is 150 and the total throat area is 250 multiplied by TT multiplied by 2 because we have two such welds. Okay. So this is the value we got for F1. Next, we need to find out what is F2. Again, from the bending equation. So PUE divided by IXX, Y max is the distance of the largest weld from the neutral axis. Okay. So M is nothing but PUE. That is also calculated. Y max is 62.5. So that is, this height is 125. Okay. This is the neutral axis. So the distance of the farthest weld from the neutral axis is 125 divided by 2, that is 62.5 millimeter. So that's what I have taken here. And IXX, yes, 2 times about this axis, BDQ by 12, that is 250 multiplied by TTQ by 12 plus apply parallaxis theorem, that is area multiplied by square of the perpendicular distance between this axis and this axis. So that is 250 multiplied by TT multiplied by 125 by 2 square, that is 62.5 square. So this is the one, and multiply the whole thing by 2 because we have two such welds. And as usual, so we ignore this part. Okay. And I got this value of IXX equal to TT. So by substituting all the values in this equation, I got the value of F2 equal to this much, 288 divided by TT. And we have this formula, and we got the stress, resulting stress, okay, in the weld, which is maximum. Okay, so I got this value. Now I'm going to find out what is the design strength of the weld. This is the stress developed due to design stress developed due to the external load. And this is the design strength of the weld, which is going to resist this stress. Okay. So we need to equate these two. Once we equate these two, I got the value of TT equal to, that is the thickness of the throat equal to 2.64 millimeter. Okay. So by equating this, so S equal to 3.77 millimeter, say 4 millimeter. Okay. So that is the weld size I got. Then what is the minimum size and what is the maximum size? So if you look here, we are providing weld here. So the minimum size of the weld go for 10.6 millimeter is the thickness of the flange here, that is, and here it is 12 millimeter. So thicker of these two thicker portions is 12 millimeter. So as per the code, the minimum size is 5 millimeter. Is it not? So minimum size is 5 millimeter. Then what is the maximum size? Maximum size is, because this is an angle where we are providing the weld here as well as here. Here we don't have any problem as far as the maximum size is concerned. Here we come across with the problem. So if you go to page number 80, look at figure 17b. So the maximum size of the weld is 3/4 of the thickness of the angle. Okay. So thickness of the angle is 12. So maximum size is 9 millimeter. Okay. That is the maximum size. Minimum size is 5 millimeter. And according to the calculation, we got 4 millimeter. Again, I repeat, we got the minimum size of the weld 5 millimeter from the table 21 on page 78, and maximum size of the weld equal to 9 millimeter as per figure 17b on page 80. Okay, so the value should fall between this minimum and maximum. Okay, we are going to provide 5 millimeter. So therefore, we shall provide a fillet weld of size 5 millimeter. Is it clear to you? So this completes the problem, and also this completes this module. Okay. So if you have any doubt, please let me know. I hope this is clear to you. Thank you, guys. And